Now in this video, we will cover section 3.4 of Dummit and Foote, which is about compositions. So first, a definition that we'll need, which we've mentioned in class, but I don't think I ever got the chance to write it down. We say that a group is simple if its only normal subgroups are 1 itself. Okay, so it's a fact that one group, the subgroup consisting of literally only the identity, and the whole group are always simple. And many groups have other simple subgroups, but a simple group only has these two normal groups. One fact about a simple group we know is that if the order of is P, then G is simple. Um, and perhaps this is easy to believe because we know that this implies that G is isomorphic to the cyclic group with P elements. And actually, the only subgroups of P are 1 and CP. So it's not that it fails to have other normal subgroups, is that it fails to have any other subgroups at all. In general, an abelian group will only be normal if it's CP. So the only simple, I'm not 100% sure what I said. If I said something wrong, I'm saying the correct thing now. The only simple abelian groups are CP prime. All the other abelian groups have more subgroups, and those subgroups are normal, so the group itself is not simple. Okay, so let's get to composition series. So definition. So let G be a group. A sequence. 1 and not. So that's the 0th group in the sequence. And not is a subgroup in 1, subgroup in 2, and so forth to K, and that one is G. Okay, so these are all subgroup symbols. So every N is a subgroup in the previous, in the next one. So such a sequence is called a composition series. If Ni is normal, Ni plus 1. So these subgroup symbols are not just subgroup symbols, but they actually should be normal subgroup symbols. And Ni plus is simple. In that case, the quotients Ni are called composition factors of G. So a philosophical thing in group theory is to think of simple groups kind of as prime numbers, because they can't be broken up into, a normal subgroup and the quotient. We'll talk a little bit about, normal subgroups and what does that mean, the quotient, etc. But anyway, so there's a philosophical reason to think of simple groups as kind of like prime numbers, in the sense that they're the building blocks for groups. And so this sequence here, this composition series, is kind of like factoring this group G into prime numbers, because you're building it up, and at every step, if you do n1 mod n naught, that's just n1 because that's mod 1. That's a simple group. And then to go from n1 to n2, the quotient is simple. So it's kind of like going up each step, is like multiplying by a prime. I mean, like not multiplying by a prime, but is multiplying by the smallest unit that we have, which is a simple group. And so, in kind of this sense, right, you can think of like the composition factors maybe prime factors of G. They're the simple groups that kind of show up in G in a certain way. And to make this analogy a little bit more precise, like why does it work? We have the Jordan-Holder theorem. So I'm actually not sure if Holder is German. In case we should say Helder. So I'm sorry if I'm mispronouncing it, and we should look into it. Don't just say that out loud. I just realized I don't remember anybody saying that name out loud to me. I'm not sure how to say it. So I'm going to say Holder for now, but that might be wrong. So this says, so let G be a group, G not one. So not just the group with one element. Then first, G has a composition series. Okay, which may or may not be a big deal to you, but it's actually not clear that this is always possible. That you can just always have, a descending chain of normal subgroups, but not just that. That actually the quotients are always simple. That you can actually build your group from all simple subgroups. So it's nice to know that it's true. So, in the analogy with prime numbers, that would be like saying like every number can be factorized as a product of primes. So here, every G does have a composition series, and then the composition factors are unique. Um, so why do I say this? Well, here in one, I say G has a composition series, and actually, G may have many. So in general, there's not a unique way to write this, and the book has several different composition series for D4 and Q8. If you want to convince yourself that a composition series is not unique, so there's many different ways to build G up in this manner, but no matter how, right, if you have two composition series, you'll get the same composition factors. um, and what do I mean, right? So what I mean is like, i.e., any two composition series of G have the same length. Right? So remember, I need to take so many steps to get up to G. Actually, this number of step depends only on G. There's not two composition series of different lengths. And then, and the composition factors are the same. So these quotients, right, are the same up to permutation. So I'm not saying that they'll show up in the same order. Right? So here, you might have, this quotient C2, and then this quotient be A5, and then in a different composition series, you might have A5 down here and C2 up here. But the point is that if C2 appears in one of the composition series, it'll appear in any composition G. And if C2 appears twice, right, as this quotient and that quotient, it's going to appear exactly twice in every composition series for G, etc. Right? So this is a lot like factorization to prime. Everything can be factored into prime, and then that factorization is unique once you reorder the primes. So this is the same thing here. Every G has a composition series, and then the factors are unique. Okay, so kind of veering into fun facts that was mentioned in the book, and I thought it was so fun I should say it. It's mentioned in the section that there are 18 families, infinite families of simple groups. Okay, so one example is C prime. So that's what I mean, right? This is a family of groups because they all share something in common. They're cyclic groups, and it's infinite because there's many primes. So there's 18 such families. This is one of them. An, when it is greater or equal to 5, is greater than equal to 5 is also simple. So, there's 18 different infinite families of simple groups and 26 sporadic simple groups. So these are just like random simple groups that don't belong to an infinite family. They're just their own person and they exist and they're simple. Another fun fact about simple groups, since they come up here, is Fate-Thompson theorem, and that comes in handy sometimes. So I'm mentioning, which says that the only finite simple groups. Sorry. So here, um, finite simple groups, 26 sporadic finite simple groups. And sorry, that was implicit, and these are all the finite. Right. So I'm not just saying like we found these, who knows what else there is there. I mean, we found these and that's it. These are all the finite. Okay. So Fate-Thompson theorem. The only finite simple groups of odd order are CP prime. Okay, so this means, right, that if the order of G is 15, then G is not simple. Like, I don't even need to know anything else about this group. 15 is an odd number and it's not a prime, so this is not a cyclic group with a prime number of elements, and so it's not a simple group. As simple as that. So that's pretty powerful to identify simple groups if that's how we're trying to get qualifying. Okay, so this is about composition series. They exist, they're there. Now I'm going to introduce a different series for groups. So it's a little confusing and it takes some work to keep track of them, but that is our task. So I'll give a definition. I'm leaving the space because to me they're not obviously, but such as a group. G is solvable if there is sequence or series, um, one, etc., all in S, G, right? So same setup with GI plus I normal in one and GI plus one mod GI is abelian. Okay, so same setup as here, right? You want like groups inside other groups, and they're all normal, and you look at the quotient. But here you want the quotient to be abelian. Okay, so the composition series is when they're simple, and simple is like prime. So it has the kind of same properties as factoring into primes. There's uniqueness of composition factor. There's well-defined length of the series. Here, all I'm asking is that these groups be abelian, so that's a lot less strict. So we're not gonna have a theorem like the Jordan-Holder theorem, right? So this series doesn't have a name because it doesn't have any good properties. I mean, the quotients are abelian, but I'm just saying, um, a solvable group might have many different ones of these series with abelian quotients, and the quotients, right, the factors of the series, they might not always be the same. It's a much wilder situation. But there is a connection, right? I mean, you got to think, like, you're basically building the same kind of thing, so there has to be a connection. So fact, D is solvable if and only if its composition factors are all groups prime order. Okay, so maybe different primes, right? I'm not saying like there's one prime, but I'm just saying that the composition factors have to be cyclic groups of prime order, and kind of what's the connection? Well, cyclic groups of prime order, those are the only abelian simple groups I mentioned, right? So it's kind of, I know that this composition series and these composition factors are unique, but at the same time, I'm telling you that G is solvable. So I'm saying that I can make one of these with abelian factors. Well, in particular, the composition series is one. So it has abelian and simple factors at the same time. So they have to be cyclic prime order. I want to note, maybe I should have noted it earlier, okay, but GI being normal and GI plus 1 does not imply that GI is normal in the whole group G. Okay, so in general, the only subgroup we know is normal is this one, like the next one, the G sub S minus 1, because it's normal. All the other ones, they're only required to be normal in the group immediately, next to it in the series. And in general, they actually will not be. Okay, so solvable groups are a huge deal, and they come up in the qualifying exams all the time. So I'm just going to end with some facts about them that you should learn and learn to love. So first, theorem, which is more of a fun fact. G is finite and solvable if and only if for every divisor n, right, that divides the order of G, such that, so not every divisor, but such that the GCD of n and the size of n for G is 1, right? So like n, and then what remains of G is relatively prime to n of the order of G. G has subgroup of order. So last time, whatever that means, making videos, but at some point we discussed how if you have a subgroup, its order will divide the size of G, but the converse isn't true, right? It's not true that when something divides the order of G, then there's automatically a subgroup of that order. But here we're saying that if you have a solvable group, then whenever n and the order of G divided by n are relatively prime, then there's going to be a subgroup of that order. So this kind of tells you, I mean, solvable is a pretty big condition. And even for a solvable group, right, there's not a subgroup of every order dividing the order of G, only not only, but the only ones we're guaranteed are the ones with this extra condition. So that's how far we are from having subgroups of order n for every n dividing G. That's a very special thing. Okay. And so now the facts. So all these facts are facts that you can always just state without proof. You can just say it. So the first one is that if n, G mod n are solvable, then G is solvable. And this relies on the fact that so that if you have 1 equal to bar, I'm just going to write the little normals here and bars, whoops, an arrow, bar, da 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 is, and here I'm talking mod n with abelian quotient, right? So exactly what it means for G mod n to be solvable. Um, so this happens if and only if there exists a sequence. So exists the sequence. There's a sequence one. Oh, sorry. Actually, that's not what I mean. There's a sequence with n is equal to n naught. It's one, two, dot dot dot, all the way is normal G with abelian quotient. So this is a mix of all the isomorphism theorems, and I encourage you to read about it more in the book. But what's important here is this fact. Whenever G mod n is solvable, then you get a little chunk of the series that you need for solvability of G, but from n. And so here in this particular case, right, if n is also solvable, then I would have like a series. I'll write this in blue, right? So if n is solvable, then I would have a series here that picks up where I have n, other stuff, and then 1. At this point, I'm running out of letters. Like I'm not, da, 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 right? So this one is n being solvable. This one is G mod n being solvable via this fact. And then if I just put these together, then I get that G is solvable. Okay? But this kind of, oh, you guys check this out. This kind, ooh, this kind of fact going from a series for G mod n to a series for G, but not really for G, just one that starts at n, is really helpful on problems. Okay, let's continue with our facts. The next fact that I want to say is that, oh, I'm bright in blue though, the homomorphic image of a solvable group is solvable. Any quotient, right? So like here, the homomorphic, I mean like any homomorphic image, right, is solvable. Any quotient of a solvable group is solvable. Um, any subgroup of a solvable group is solvable. So in particular from these two, right, we get that if G is solvable, then n and G mod n are also solvable. So, um, this fact here. Oh, I'm left on this. Okay, I'm gonna go back to this because it's too distracting. So this fact is actually an if and only if. If G is solvable, then for n, any normal subgroup, both n and G mod n, and then any homomorphic image. And then what else do I want to say? Every abelian group is solvable. Okay, and the proof is 1 is normal in G. Boom. Okay, because all I want is for this quotient to be abelian, but this quotient is G and G is abelian, so I have my series right there. So it's easy. Um, every group of order strictly less than 60 is solvable. So A5 is the smallest solvable group. Um, every non-abelian simple group, non-solvable, and the proof is this again, right? Because the only normal subgroup of a simple group is 1, and the quotient is G, but G is not abelian. And so this is not a valid series, so it doesn't work. G is not solvable. And then the last one, Burnside's theorem, if the order of is to the A to the B who are primes, then is solvable. It's a very strong theorem. And in particular, here, A or B can be 0, i.e. if the order of G is a power of a prime, then um, and the groups with this property that the order of G is a power of a prime is called a P group, and we'll study those briefly later in the semester. So that'll come up again. Actually, I don't know why I turned the page because those are all my solvable group facts. Many of these, with our current level of technology, are actually difficult to prove, except the little proofs that I gave. But later in the semester, when we study commutator subgroups in the lower series, we'll have a different way to characterize solvability, and all of these will be easier to prove. So I'm gonna wait till then. Ooh, and actually, worth it to make a new page, just in case you're reading different sources on this. Soluble is the same as solvable. I think maybe one of them is like more German origin and the other one is more French in origin, but they both mean the same thing when the groups. So don't. I'll always use solvable, but if you're, like I said, if you're looking elsewhere, you might see the word soluble. All right, that is it for composition series and